In chemistry, hydrophobicity is the physical property of a molecule that is seemingly repelled from a mass of water. Hydrophobic molecules tend to be non-polar and, thus, prefer other neutral molecules and non-polar solvents. Hydrophobic molecules in water often cluster together, forming micelles. Water on hydrophobic surfaces will exhibit a high contact angle. Examples of hydrophobic molecules include the alkanes, oils, fats, and greasy substances in general. Hydrophobic materials are used for oil removal from water, the management of oil spills, and chemical separation processes to remove non-polar substances from polar compounds. Hydrophobic is often used interchangeably with lipophilic, fat-loving. However, the two terms are not synonymous. While hydrophobic substances are usually lipophilic, there are exceptions, such as the silicones and fluorocarbons. The term hydrophobe comes from the ancient Greek delta rho omicron phi omicron beta omicron sigma, having a horror of water, constructed from delta omega rho, water, and phi omicron beta omicron sigma, fear. Chemical background. The hydrophobic interaction is mostly an entropic effect originating from the disruption of the highly dynamic hydrogen bonds between molecules of liquid water by the nonpolar solute, forming a clathrate-like structure around the nonpolar molecules. This structure formed is more highly ordered than free water molecules due to the water molecules arranging themselves to interact as much as possible with themselves, and thus results in a higher entropic state which causes nonpolar molecules to clump together to reduce the surface area exposed to water and decrease the entropy of the system. Thus, the two immiscible phases will change so that their corresponding interfacial area will be minimal. This effect can be visualized in the phenomenon called phase separation. Research and development. Detra and Johnson discovered in 1964 that the superhydrophobic lotus effect phenomenon was related to rough hydrophobic surfaces, and they developed a theoretical model based on experiments with glass beads coated with paraffin or TFE telomere. The self-cleaning property of superhydrophobic micro-nanostructured surfaces was reported in 1977. Perfluoroalkyl, perfluoropolyether and RF plasma-formed superhydrophobic materials were developed, used for electrowetting and commercialized for biomedical applications between 1986 and 1995. Other technology and applications have emerged since the mid-1990s. A durable superhydrophobic hierarchical composition, applied in one or two steps, was disclosed in 2002, comprising nano-sized particles 100 nanometers overlaying a surface having micrometer-sized features of particles 100 micrometers. The larger particles were observed to protect the smaller particles from mechanical abrasion. In recent research, superhydrophobicity has been reported by allowing alkyl ketene dimer to solidify into a nanostructured fractal surface. Many papers have since presented fabrication methods for producing superhydrophobic surfaces, including particle deposition, sol gel techniques, plasma treatments, vapor deposition, and casting techniques. Current opportunity for research impact lies mainly in fundamental research and practical manufacturing. Debates have recently emerged concerning the applicability of the Wenzel and Cassie-Baxter models in an experiment designed to challenge the surface energy perspective of the Wenzel and Cassie-Baxter model and promote a contact line perspective. Water drops were placed on a smooth hydrophobic spot in a rough hydrophobic field, a rough hydrophobic spot in a smooth hydrophobic field. and a hydrophilic spot in a hydrophobic field. Experiments showed that the surface chemistry and geometry at the contact line affected the contact angle and contact angle hysteresis, but the surface area inside the contact line had no effect. An argument that increased jaggedness in the contact line enhances droplet mobility has also been proposed. Many hydrophobic materials found in nature rely on Cassie's law and are biphasic on the submicrometer level with one component air. The Lotus effect is based on this principle. Inspired by it, a lot of functional super-hydrophobic surfaces were prepared. An example of a biomimetic super-hydrophobic material in nanotechnology is nanopen film. In one study, a vanadium pentoxide surface that can switch reversibly between super-hydrophobicity and super-hydrophilicity under the influence of UV radiation is presented. According to the study, any surface can be modified to this effect by application of a suspension of rose-like V2O5 particles, for instance with an inkjet printer. Once again, hydrophobicity is induced by interlaminar air pockets. The UV effect is also explained. UV light creates electron-hole pairs, with the holes reacting with lattice oxygen, creating surface oxygen vacancies, while the electrons reduce V5+ to V3+. The oxygen vacancies are met by water, and it is this water absorbency by the vanadium surface that makes it hydrophilic. By extended storage in the dark, water is replaced by oxygen and hydrophilicity is once again lost. Potential applications. Active recent research on super-hydrophobic materials might eventually lead to industrial applications. For example, a simple routine of coating cotton fabric with silica titania particles by sol gel technique has been reported, which protects the fabric from UV light and makes it super-hydrophobic. Also, an efficient routine has been reported for making polyethylene super-hydrophobic and thus self-cleaning. 99% of dirt absorbed on such surface is easily washed away. Patented super-hydrophobic surfaces also have promise for lab-on-a-chip microfluidic devices and can drastically improve surface-based bioanalysis.